So previously we talked about a type of motion called transport, and this is drift, the kind of thing that you see when there's a current in the water or in the air, and everything sort of moves along together at the same rate. Another kind of motion that's fundamentally different is diffusion, and this is what happens when the net result of a whole bunch of little random motions cause something to sort of spread out. So suppose you were to take a bunch of red dye and pour it into a tank of pure water. Then you would see that the dye would spread from regions of higher concentration to regions of lower concentration. And the bigger the difference in the concentration, the faster the flux. And so this is the observation that goes behind Fick's law. So if we look at basic transport, this comes from the conservation equation u sub t plus phi sub x equals 0, when we make the assumption that the flux is proportional to the density, right? So that's one constitutive equation. So remember, constitutive equation this is something that relates the flux to the density, and it depends on the particular material or system that we're looking at. But there's another one, and that comes from Fick's law. So Fick's law states that flux is proportional to the negative of the density gradient. So it flows down the gradient. So this means flux is, and then we say proportional to the negative of the gradient of the density. And so in one dimension, this just means that flux looks like minus d times the x derivative of u. So when we substitute this into the conservation law, this gives ut minus duxx equals 0. Okay, and so this one right here is the diffusion equation. And and so if you just look at the form of this equation, what does it say? So ut equals duxx. So this is telling you in words that speed or velocity is proportional to curvature or concavity or convexity, however you want to phrase it. But the second spatial derivative, that represents curvature, right? So if if uxx is positive, then that means that the graph is concave up, yeah? And so if the graph is concave up, then at that point it will be moving upward. And if the graph is concave down, then in that region it would be moving downward. So it produces a flattening effect. So diffusion is naturally sort of an averaging operation.